Hey data junkies, welcome back. This is your host Shawn Janzen, and we are continuing steaming right along onto our one-way ANOVA analysis of variance journey. We are now on video 7, and this particular one is going back to do another example here. We're not going to have the munchkins this time. We're going to deal more with credit loans in this particular one, so something a little less fantastical. And we're going to do this in R, and we're going to show you some different options and alternatives, bringing together and stitching together some of the different things that we've been talking about in the previous videos. So let's go ahead and talk about some peer-to-peer lending and the credit that gets extended. So just to kind of give you a little bit of a setup here, peer-to-peer lending was believed to help people out to get individuals who might not be able to get traditional loans from banks. So groups of people would come together and issue each other credit, but there has to be some sort of judgment about who gets credit to be trusted to repay a loan and things like this. And so when you have people making judgments about other people, things like human error can come into play, discrimination come into play, things like this. So let's go ahead and take a look and ask ourselves that when lenders consider how much to give people with credit card debt, does it matter whether or not that the borrower rents, owns a home outright, or owns a home but is still paying a mortgage? Each of these things, your home is typically a major component of your financial system and your socioeconomic status. So does your home status affect how much you might be able to get in credit? The null hypothesis is going to tell you that there's no difference in these population means. It doesn't matter on average if you have a mortgage, a rent, or if you own, that it's going to determine how much credit you get. The alternative hypothesis, we're using the ANOVA framework here, says at least one of these differences at the means, one of these are going to be different at the population means. So one of the average for mortgages or renting or owning is going to be different. They all could be different from each other, but we're saying at least one of them is for the alternative. So we're going to spend a quick moment getting to just kind of look at our data. All right, I'm going to be providing for you a credit card loans CSV file. You can import that in. I'm calling it loans in this particular example, and I do a structure on it. It tells me I have 400 observations across 3 variables. One of them is a member ID number, so we're really not going to use that. But the other 2 are the amount that's been funded, so how much credit was given to the person, and then the other one is a home ownership status variable, again identifying if they rent, own, or mortgage. So let's go ahead and spend a little bit more time getting a look at the data. I'm going to look at a frequency table here for the home ownership. So out of the 400 I have relatively equal sample sizes between mortgage and rent at 184 and 188, but my home ownership is a tiny amount relative to them, and only 28 comparatively. 7% of the overall sample size of 400. So this could become a little problematic when we get to the rest of the analysis later. Some of you that like to jump straight into your tests, always make sure you're doing your descriptive statistics first, because you can see little things like this that could trip you up later, and it's better to know where your hang-ups might come from or where your trouble might come from before you find that trouble. So let's go ahead and take a look at the dependent variable. This is the amount that someone was funded. So I've done a Desker out of the summary tools library here. Again, out of 400, we aren't missing any values, so all 400 are here. And we can see that on average, someone had received $35,000 in credit. The median value was much smaller at $12,000. I'm sorry, I misread the wrong line there. So the median value was $12,000. The mean value was $13,665. I read you the max value previously. So in this case, we still have a mean that is higher than our median, and so there is the potential for some skew here. We do have a skew statistic and whatnot, so we can definitely see where some of the spread is going on, but let's see how it looks when we put it into the context. So let's just jump straight into some of our other tests here. Homogeneity variance. Do we have equal variance across our groups? I'm using the Levine's test. Loan amount tilde onto the home ownership, centering it at the median. I'm choosing the median right away because I had these unequal sized groups, and I want to see how these compare out. So I get the Levine's test. It tells me I have a p-value that's extremely small at 0.0007 and change. That's far below my alpha of 0.05 that I'm going to be using here. So I'm going to reject the null of the variance test and say that I do have unequal variances. Now, keep in mind, this median is giving me the Brown-Forsyth, not technically the Levine test, but I'm going to go, just for sake of purposes here and showing you the code, show you how this would look if I did this with the mean. So I'm going to repeat this test, and I'm going to use it with the mean instead of the median, and I'm going to get an even smaller p-value at 0.0002 and change, And so we can see comparatively at these ridiculously small p-values, I'm getting pretty much the same results that I'm rejecting the null hypothesis, and I have unequal variance regardless which of these tests that I'm using. But the median was the more robust of the two, and I was using it because I have a nice large sample size of 400, so I could get away with using it. Now I'm going to move on to the normality test here. So I've taken these values that I have, and I'm plugging them into an AOV function. I'm saving that into an object called AOV loans. And I run a QQ norm on AOV.loans and a QQ line on AOV.loans. And lo and behold, in my normality plot, the middle's tracking pretty well, but on the ends, I've got some skew, right? On the bottom part, the tail's starting to rise up. That's an indicator. If this happened to be put out into a histogram, this would show you that there's a tail leading out into one direction, and that there's a bump on the other side as well. So this is the presence of a spike in the data coming up as well. So there's definitely some non-normality starting on here. It's not terrible, but it's not good either. Look at the x-axis. When you're looking at these these normality plots, they're called normality probability plots. They're also called QQ plots, which is what I call them. Depending which forums you read, you're going to see them referred to back and forth. But keep in mind, these are standardized theoretical quantiles down here. So they're centering at 0, and they're going out positive and negative on the left and the right. And you would think that the majority of your dots that are tracking in the line are within that plus and minus 2 there. So keep those in mind as sort of like frameworks to find out like where some of your normality is really starting to deviate. Is it just in the tails, or is it in some of the body of the line as well? And so, yeah, we definitely have some issues starting to go on here. It isn't terrible, but it's not good. So, again, I'm just going to kind of recap then and look at some of my hypotheses now that I've checked through these different assumptions. And I said I've got 3 groups: mortgage, owning, and rent. And I have the mean loan amounts for each one of these. Mortgages got about 15,430. Homeowners got 10,000, about 600. And renters got about 12,400 rounded. And I have the standard deviations for those. So now that I'm looking at these differences in means and I have their standard deviations, I'm going to reflect again on my hypotheses that all of these means are going to be equal. Maybe. I mean, they're within $5,000, $6,000 of each other, which in the scheme of things and the amount of some of these loans isn't that big of a difference, but it kind of is at the same time. So a lot of this happens to be in context. I think that these means are far apart from each other, but we have to take into account their standard deviations and the variation between and within these groups as well to see if they're actually statistically different. So let's go ahead and move in to calculate the test statistic. So here I am running the AOV function, and I've gone the long way just so you can kind of see this on this particular one. I'm doing just the AOV function, not the summary on it. It's giving me the degrees of freedom and the sums of squares. I can divide each of those degrees of freedom into their respective sums of squares to get the mean square for between and within. Once I get the mean square between and within, I'm going to divide those to get the F statistic. Now I'm going to introduce you to a couple extra functions here, the QF and PF. QF and PF. QF gives me the critical value for an F distribution, and PF gives me a P-value for an F distribution. This falls right in line with our family of other functions that we've been building out, such as QT and PT, Q norm and P norm, Q chi-square, P chi-square. So there's this pattern going on I'm hoping you're starting to pick up on. So when we're in the QF function, I specify it with saying at what probability that I want to be using. So here's where I'm specifying my alpha, comma my degree of freedom for the between, comma my degree of freedom for the within, then lower dot tail equals false because I'm looking out in the right tail. This is a right tail type test, bounded at 0 on the left, and this is going to tell me that my F critical value is about 3.081. So I'm going to round it to 3 for purposes of the video conversation here, and my my critical value of 3 is much smaller than the F statistic I obtained of 11. So that tells me right off the bat I should be statistically significant. Let's go ahead and look at the P-value as well. I do a PF function, and in there I plug in the F statistic I obtained, my 2 degrees of freedom, and again a lower tail equals false. And I have a P-value of 2.198 E negative 0.5, which is ridiculously small and far under my alpha of 0.05. So again, validating that I'm statistically significant. Now, just doing that by hand, I'm just going to go ahead and plug my AOV as well into a summary here and show what I have. And so this is going to generate out some of these particular values here. So I have the summary table, and it tells me here's the F statistic I just calculated by hand and the p-value. I did these by hand just so you can kind of walk through and see how that works in practice, but for general day-to-day stuff, just plug it directly into the summary and get the results here for you straight off. So I can see that we are statistically significant with our F statistic, and I have the values that I can use to go ahead and report it. Now when I'm reporting this is going into the APA citation style, so I'm doing F, and then my 2 degrees of freedom, 2,397, equals my F statistic of 11.02, and then my p-value is smaller than my alpha of 0.05. The p-value I obtained was far too small to do a p equals, so I'm doing p is less than my alpha. If I really wanted to, I could set it as a lower alpha just to show that it was highly statistically significant, but it just depends on what it is you're reporting in the context that you want to write with. So from there, I said, all right, I'm already statistically significant. Let's go ahead and find out where these differences are. So I'm going to plug my analysis into the Tukey HSD, and it's going to tell me here that I have my differences. I have 3 pair of differences: own mortgage, and rent own. And of those, there was no difference between looking at the p-value between the renting and the owning. And so the bottom relationship there had a p-value of like 0.43, so I'm going to put that to the side a moment and focus on the other two. What do the other two have in common? Well, they both have to do with people who mortgage. All right, so they both deal with people who mortgage. Let's look at the differences. Own minus mortgage is a difference of about negative 4,800. Rent minus mortgage, that's a difference of about 3,000. So in both cases, they're statistically significant. Mortgage was second, and the differences were negative. So we're finding that people who are mortgaging their homes are getting less credit on average than people who own or people who rent. Now, what that means specifically for the credit issuing market, I'm not exactly sure, but we would take that to the decision makers who are making those sorts of decisions and find those particular things and see what they have to say for it and get the additional context that we need for the analysis. But these are the patterns that we need to be finding. I'm going to put this into a visual for you as well, so I'm taking that AOV loans into the Tukey HSD, into the plot. It's going to produce for me this graphic here, and I can see that the rent-own confidence interval is spanning that vertical line of no difference, and that the other two are on the negative side with mortgage on the second variable in subtraction. So it's showing the exact same thing, just graphically speaking, from what we had before. So wait a minute. Hold on. I just did, and you let me get away with. You didn't say anything. I just did an AOV and the summary function version of the one-way ANOVA. But when I did my assumptions, I had unequal variance issues, and I had questionable normality. Should I have been using the other version with the AOV function? Well, that depends on where you're coming from. So I should be using the Welch ANOVA to deal with my unequal variances, but I couldn't get access to the Tukey differences there. So in terms of the raw mean differences, I could go ahead and look at the Tukey just to get the mean differences, to get the quick visualizations, but I shouldn't always necessarily trust the p-values that I was seeing coming out of those and trust the F statistic coming out of the summary. I can use it as a baseline, but I should be checking the Welch ANOVA as well, because that's the one that's going to be correcting for my unequal variances. So let's go ahead and switch gears to the Welch ANOVA. So the Welch ANOVA I said was in the one-way.test, and I'm plugging in my loans amount, fund tilde with my home amount. And I note that the default setting is already set to unequal variance, so I don't need to do any additional work there. And the results I get an F statistic of 13 something. My previous F statistic was about 11, so it's already different there. Degrees of freedom are 2 and about 92, and another ridiculously small p-value. So I'm getting statistically significant results regardless of which version of the ANOVA I'm using. But I do need to keep in mind which one I'm looking at and why, and how I get that straightened out. Now, I want to go ahead and just show you the Kruskal-Wallis to begin with, just so you can see how it looks like with the code. I had enough variance issues here that I'd probably be sticking with the Welch ANOVA in these particular choices here. I didn't have crazy normality issues that would really want to push me into the Kruskal-Wallis component. But we're going to show you this just so you can kind of see how it looks. So I'm doing the Kruskal.test on the funding amount tilde to the home ownership, and it's going to produce for me a Kruskal-Wallis rank sum test result. and it's going to tell me that I have a Kruskal-Wallis chi-squared of about 18.5 with 2 degrees of freedom and another ridiculously small p-value. So keep in mind I said this is going to report a chi-square, but we're going to treat this as an H statistic. So I'm going to, before I do my write-ups here, I'm also going to show you the pairwise test. I said before that if you go ahead and do a Welch ANOVA, or even if you're doing a Kruskal test, and you want to just get a general sense of the pairwise differences, are they significant or not, this is where we can use the pairwise.t.test. I'm going to plug in the same variables I had before with my funded and my amount. Note this time I believe they're separated by a comma, not a tilde. So keep that in mind when you're checking your code. If you happen to get some errors, check to see your commas and your tildes. And then once I have those, I'm going to add in another option where I have p.adjust equals method. And this is where I specify the Bonferroni. Tukey is not available with this particular one. There are many other methods you can plug in, but the Bonferroni is going to be the one closest to what we were dealing with before. It's just going to have a little bit more conservative opinion about which ones it's making statistically significant. And it's going to generate for us out at the bottom a pairwise comparison with set of t-test results. And I see that I get a little half matrix here. So the mortgage own is statistically significant. These are just p-values, not differences in means. The mortgage and rent also statistically significant, but rent and own not. So again, this is following the same sort of p-value results that we had with the Tukey result, and I could still use that Tukey just to get a visualization for the differences in means. Even if I wasn't getting those p-values, I could still look at the differences in means because those weren't getting adjusted on how they were being calculated. Those just one score minus the other. So going now, I just want to go ahead and finish the write-up here with the Kruskal-Wallis test. I have the Kruskal-Wallis, I have the scores up at the top, and I'm going to say that I ran a Kruskal-Wallis rank sum test of an H with 2 in parentheses for the degrees of freedom equal to 18.5, and P in this case I'm making as P is less than 0.001 to show that it was a ridiculously small p-value. Too small to write as a P equals. Don't write it in scientific notation. And if I want, I can compare this to the result I had from the Welch test that said of the peer-to-peer loans F, I had, in fact, that should say Welch's F has 2,92 degrees of freedom, 13.5, and also ridiculously small. So this is just a second example walking through with R, adding in some of the extra things that we've been learning about in terms of Welch and Kruskal-Wallis and the pairwise tests. So extra little bits for you to learn about and practice and use. So at that point, I'll see you all in the next video where we're going to wrap up with effect sizes and power analysis. I'll see you then.